So in this video we're going to be talking about compound interest, geometric sequences, and exponential growth. So first off, let's start off by writing the formula for compound interest. So we have the amount is equal to principal multiplied by 1 plus interest to the power of n. Now let's relate that to the formula for a geometric sequence. So for geometric sequences, the term number is equal to a times r to the power of n. So let's look at some similarities between this and this right here. Because this formula, the formula for compound interest, is actually derived from the formula for geometric sequences. And you can see that they do look very similar. So first thing we can notice from here is that the amount in compound interest is essentially the same as Tn in a formula for geometric sequences. The amount is equal to the term number. The next thing we can see from these two, when they are put side by side, is that the principal is also the same as a, or the first term, in the formula for geometric sequence. And that makes sense because the principal is the initial amount you put in, the first payment, and a for geometric sequences represents the first term in the sequence. So those two relate together. And finally, actually let's go on to the exponent. The exponent n here and n here, that's pretty obvious. So n here is the same as n here. The number of compounding periods is the same as the number of terms for compound interest versus geometric sequences. Finally, let's look at the r term, the common ratio. And from this, it's not very obvious when you first look at it, but once you cross out everything else, a is equal to Tn, p is equal to a, and n is equal to n, you get 1 plus I for compound interest is the same as r in geometric sequences. And that makes sense because the interest rate is essentially what the principal is growing by. It's what's multiplied to each term to get the next term, which is also what the common ratio is. And when this pattern is graphed, let me just draw a quick graph here. When all the values for compound interest are graphed, they form a graph that looks kind of like this. Oops, that's a little too steep, but let's just go with it. They form a graph a little like this. And this kind of graph is called an exponential growth graph because the values are the previous value is multiplied by a common ratio to get the next value, and each subsequent value is greater than the previous value, many times greater. So in the end, you end up getting this. And the thing with exponential functions is that they always contain the variable. Let's say the variable is x. The variable is always an exponent. So let's say that y is the base. This kind of function always has a variable as the exponent to the base, which is what leads to this curve right here, this ever steepening curve. And when graphed, both compound interest values and the values for geometric sequences would form this kind of graph, which, as I mentioned before, is called an exponential graph. So that's it for this video. It's a pretty short video, and in our next video we'll talk about some other things relating to the toolbox.